Howdy, y'all. This is going to be a follow-up to yesterday's FRQ, number 8. That's on flower opening, flower color. That's not a P. I'm not Ross Ryan. Not doing any power opening, just talking about flowers. And then number 2, standard water potential experiments. Data representation and graphing that tends to show up on the AP exam because College Board loves this shit. All right. No more swearing, promise. Try my hardest. Number 1 is going to be solutes in the bag. Number 2 going to be potato slices in different concentrations of solutes in the environment. Number 3 is going to be a reminder that you had on review guide, I think it was 1. Number 9, worth looking at because it relates to the current topic, which is water potential. All right. Oh, here we go. This FRQ is a little bit confusing because you got hydrogen ions, you got potassium ions, and they're moving in different directions, and it kind of depends at what the pH is and the flower color, and you're thinking, all right, so we're looking at how a bud opens up. I think this is absolutely beautiful. By the way, imagine a bud opening up into a flower because its cells swell. How does a living thing enable the cells to swell? It works hard using ATP energy to pump ions into a vacuole, already a watery space, but pumping ions into the vacuole isn't its goal, boys and girls. Getting water to move in is its goal. And you can imagine this beautiful flower opening. Going to happen pretty soon all around you if it hasn't already because it's springtime. All right, so I'm going to go straight to the answers, which means I need you to review the prompt if it's not fresh in your mind. Deal? All right, answer to part A. Identify the cellular component. 1 point. Got to put in a complete sentence, so see, I'm getting better at that. It's responsible for the increase in the vacuole's pH because it moves hydrogen ions out of the vesicle. All you have to do is identify it. So you could put your period here if you wanted. I elaborated for the sake of reviewing with you that concentration of H plus correlates to decrease in pH. So the reverse would be true. If we decrease the concentration of H+, then the pH of the vacuole is going to increase. Part B. Provide reasonings to support this claim. This is all you had to have, y'all. As a solute concentration increases, solute being K+, because that's what they're pumping in. K+ right here, bringing K+ in from the extracellular environment, pumping it into the vacuole. What happens? The vacuole becomes hypertonic, causing water to move into the vacuole. And then I had to make it look fancy, promoting swelling and thus flower opening. Now, the prompt has a little bit to do about flower color, and I get that. The pH of the vacuole correlates to the color of the flower being blue instead of red. But this is all they wanted. The vacuole becomes hypertonic, causing water to move in. What's another way to say that? The vacuole water potential, and remember, you can't use a symbol. You have to say in words, water potential. Decreases with more solute. What that means is it becomes more negative. Sorry. You guys know that as water potential decreases, oh man, there we go. As water potential decreases, water is more likely to move into the area. More solute, lower water potential, more negative number, water's more likely to move. All right, go and take a deep breath. Moving on to the next one. Email me questions if you want, based on, based on how annoyed you get by all this. I'm not annoyed teaching you, but can be annoying, right? So, for you that is. Here's a classic way the College Board likes to put experiments in data tables and graphs and stuff like that. They'll put the solute in a model cell called a dialysis tubing, which basically looks like a bag. We made them. You guys measured them. You remember that? The dialysis tubing, or the bag, has a semi-permeable plastic used to make it. So then they'll give you 3 scenarios. The solutes in the bag. What's a solute? Sucrose. Solutes in the bag. It's put in different environments of distilled water. You know what's going to happen. Water always moves to the area of higher solute concentration, which because there's 0 solutes in distilled water, water's going to move into all 3 bags. So why'd they even make 3 situations? Well, because they want you to think about water potential, which is the likelihood or a numerical way to express the likelihood. I don't know if that's how you spell it. I'm having trouble now, but the likelihood of water to move in a certain direction. Okay? Water's going to be more likely under different situations. Okay, let's take a little bit of a look at that right now. Okay, water potential equals pressure potential plus solute potential. This, we always assume, is 0 unless given. That's annoying, right? Usually they say these experiments are done in open containers, meaning there's no pressure applied to the system. So we just get rid of it unless they give it to us, which I don't think they will. And then we look at solute potential. Solute potential is negative ICRT. And you will be given a formula sheet, but I don't think you'll have to calculate this. I just think you'll have to understand it. So what is water potential? The likelihood of water to move. What's it based on? Well, here's concentration. This is a constant, so it doesn't really matter. This is temperature, in Kelvin. And this is the ionization constant. The only 2 ionization constants I've ever seen the College Board ever care about are the ionization constant of sucrose, which is 1, and the ionization constant of salt, which is 2. More on that in a minute. The concentration of the solution, that's going to be given to you in the problem. This is a constant. This is the temperature, usually 25 degrees Celsius, which 298 K. This is not going to be that much of an important unless the experimental independent variable is temperature measurement. Most important measurements are whether it's sucrose or salt and then the concentration thereof. All right. So, back to this. You guys are smart. You know math. As the constant of ionization gets bigger, like for salt, this gets more negative. Water's more likely to move into that area. As the concentration gets greater, this gets more negative. Water's more likely to move into that area. So if this is the likelihood of water to move, when water potential is more negative, water wants that. Now, don't use that language on the AP exam. When I say water wants that or wants to get there, I mean that there's a greater likelihood of water traveling to that area because water moves from high to low water potential. Water potential of pure water is 0. So as the water potential gets more negative, water's going to be more likely to move there. I know this is annoying. I know it's a lot to keep in your mind. I'm just trying to remember you. Well, not remember you, but remind you of it and then encourage you because I'm proud of you and I know you can get this right. So what are we going to graph for this experiment? What's your independent variable? Right now in class, Evan trying to help me out, even saying the wrong answer if he needs to, just because he wants to end the silence. I guess he'd be right this time though, because he's prepared, right, Evan? So independent variable is going to be concentration of sucrose, and that's going to be in molar measurements. Dependent variable is going to be percent change in mass. Now, I don't think they're going to make you come up with those, but you have some experience in the laboratory figuring this out, so own it. What's going to happen? Well, more water is going to move into this guy than this guy, and more water is going to move into this cell than this cell. So we're going to get something that looks like this. Okay? As a concentration of sucrose in the cell increases, the percent change in mass is going to increase, going to gain more mass. Now, here's number 2. College Board really likes this scenario also. Instead of putting a bag like a model cell, we're putting potato slices. We did this too. And instead of putting the potato slices in distilled water in a beaker, we put potato slices in distilled water in one beaker, then 0.2, then 0.4, 0.6, varying concentrations of sucrose. Now, what would happen if this sucrose was salt? The percent change in mass would be greater. Why? Because the water potential would be lower because salt has an ionization constant of 2. All right. Anyway, it's in sucrose. Gains, loses. We know that this must correlate to the hypo/hypertonicity of the environment. Because if the cells are gaining mass, it must be that distilled water has less solute concentration than the potato cells themselves, right? All right, so here's what it looks like. Percent change in mass over concentration of the sucrose in the beaker. We're going to get a different relationship because the cells are either going to gain, and these two concentrations, 0 and 0.2 molar, or lose in these 3-4 concentrations. Okay? And the value of this is that we can interpolate, meaning we can look on the graph where the line crosses 0, and we know that that means 0 gain or mass, even though we didn't have a data point that resulted in 0% change in mass, we can predict that that would be somewhere in between 0.2 and 0.4, otherwise known as 0.3. That would be the osmolarity of the potato core cells. What does that mean? It means in nature, as potatoes just sitting out there in the ground, they're sitting there with about a 0.3 molar cytosolic solute concentration. And then sometimes College Board likes to make you calculate the water potential based on that number. So you go, oh, open container, yeah, boy, not putting the potato under pressure. That'd be dumb. So forget the pressure potential. Y equals negative ICRT. This is going to be 1. This is going to be 0.3. This is going to be the constant, which is going to be given to you. This is probably going to be room temperature, 298 K. You can use that. The value, we call this the x-intercept, to calculate water potential. Now, I want to show you the top of this. I think this is part of one of your review guides. I'm not sure which it is. I want you to look at 9, 10, and 11. I want you to pause it. I think you'll understand it. This is a lot. You guys are amazing. I'm so proud of you. I don't expect you to take this all in one day at all. I just want to really give you tiny tidbits of information that may help your memory come back to life. Because last semester we had a good one, right? This semester we're having a good one too. All right. Email me with any questions. The very last thing I wanted to show you was that in Review Guide 1 there was this. This is the answer key. This is another representation of how the College Board likes to spin this stuff up for you in an experiment. Okay, you had to make the graph. You won't have to do that this year, but then you had to describe. And so please go back earlier in the calendar to the resources that you have relating to how the College Board likes to tackle water potential. And that's all. Love you guys. Bye.